Hello, and thank you for viewing this presentation. My purpose here is to provide an overview of why many scientists and policymakers believe that an emerging set of technologies and processes, collectively known as carbon dioxide removal approaches, or CDR, may have a critical role to play in climate policy making. So let's start off with a roadmap for this presentation. So first of all, I will provide a working definition of carbon dioxide removal and what is not carbon dioxide removal. Second of all, I'll talk about the primary reasons to pursue carbon dioxide removal. Third, I'll talk about the current status of the carbon dioxide removal market. And then finally, I'll talk about how much collective carbon dioxide removal we will need through the middle of the century and through the end of the century. So first of all, let's start off with discussing what is carbon dioxide removal. And I'm going to start off initially with a working definition and then pick apart some of the key components of this definition. So carbon dioxide removal, according to the Intergovernmental Panel on Climate Change, in its 6th assessment report, refers to anthropogenic activities, so those are human activities, that remove carbon dioxide from the atmosphere, right? So these are legacy emissions of carbon dioxide that have already been released into the atmosphere through processes such as the burning of fossil fuels, the operation of our cars, and the operation of factories. And durably storing. Durable is a term that's contested. Some policymakers and scientists believe that to be durably stored, carbon dioxide has to be stored for a period that's commensurate with the time that carbon dioxide that's released through the burning of fossil fuels, for example, will remain in the atmosphere, which in the case of at least 20% of carbon dioxide can be 1,000 years or more. Others are a little more lenient and define durable as a couple of 100 years, for example. And then store it in geological, terrestrial, or ocean reservoirs, right? Geological and terrestrial it can include land-based places such as, for example, abandoned coal mine seams or saline aquifers, or under the ocean. Or it can be utilized, the CO2, in products to produce, for example, hydrogen, or to incorporate in concrete production, or for high-strength materials. Now, why do we want to engage in carbon dioxide removal? And this is related to our basic science associated with climate change and the greenhouse effect, right? So incoming solar radiation, which is in a short wave side of the radiation spectrum, easily reaches Earth. It penetrates. Some of this radiation is absorbed by Earth. Some of it, however, in now a longer form of radiation, seeks to escape back to space. But because its wavelength has changed, it can be trapped by so-called greenhouse gases in the atmosphere. And when it's trapped, it's then re-radiated back to Earth, and it can exert a warming impact. So the idea of carbon dioxide removal is to remove some of those greenhouse gases that trap that outgoing radiation, meaning that more radiation escapes to space, and that reduces overall ambient warming, or what we call radiative forcing, the balance between incoming radiation and outgoing radiation. Carbon dioxide removal approaches are usually loosely categorized as either natural, combined or mixed, or technological or novel. And these are some examples, and I'm not going to go into great detail about these approaches because I'm going to do that in a subsequent lecture, but I'll talk a little bit about these, right? So natural approaches include things like afforestation and reforestation, planting trees where they haven't existed for at least 100 years, or planting trees where they've existed in less than 100 years, afforestation or reforestation. And of course, planting of trees can take up CO2, utilize it in the photosynthetic process, and thus remove carbon dioxide from the atmosphere. Soil carbon sequestration, right? Reducing the amount of CO2 that is released from soils or taking up more CO2 in soils. Combined approaches utilize both technology and natural approaches, bioenergy with carbon capture and storage, right, which utilizes bioenergy feedstocks, things like corn or wheat, or dedicated energy crops such as switchgrass or miscanthus to take up CO2. When that biomass is burned, it would release the CO2 back into the atmosphere, but we use a technology called carbon capture and storage to capture that CO2 when it is combusted, and then that CO2 can be pressurized into a supercritical state, and it can be conveyed through things such as pipelines to be stored terrestrially or in oceans, or it can be utilized. And then we have what we call technological approaches, right, that utilize technologies primarily as our way of achieving carbon removal. Direct air capture, for example, utilizes fans that force CO2 through filtration systems that separate out the CO2 and facilitate conveying it to areas for storage or, again, utilization. Or ocean-based approaches, for example, that can facilitate the uptake of CO2 in the ocean, conversion into other forms such as carbonates, which allows more CO2 to enter from the atmosphere, drawing down CO2, or approaches such as seaweed harvesting, which facilitates photosynthesis, much as trees do on land. And again, we'll talk about all of these approaches in more detail in subsequent lectures in this series. An alternative way to categorize carbon removal is carbon removal based on the form of storage by the processes we're using to facilitate carbon removal. So we have processes that involve carbon removal to the biosphere, right, which encompasses all living things on Earth. This, again, includes things such as afforestation and reforestation, and some of the approaches associated with marine-based carbon removal, such as seaweed sequestration, or again on land, soil carbon sequestration, or the second category, carbon removal to the geosphere, right, which is defined as all solid parts of Earth's crust. And this can involve enhanced mineral weathering, right? The idea that if you weather silicate minerals, for example, they can take up more CO2, convert it to carbonates that ultimately end up in the oceans and used by shell-forming species, and thus reduce ultimately CO2 into the atmosphere. And again, you'll see various discussions of how to categorize these approaches, but this will give you an idea of the primary ways that we do this. It's also important at the outset to define what carbon dioxide removal is not, right? And so I want to talk about 3 or 4 primary things that carbon dioxide is not. The first is carbon dioxide is not avoiding emissions from actually occurring and releasing carbon dioxide into the atmosphere. So, for example, if you utilize solar energy or wind energy to produce energy, instead of burning fossil fuels, which is certainly a salutary thing to do and should be job one, in my opinion, that is not carbon dioxide removal. It does not remove carbon dioxide that has already been released into the atmosphere, but instead it ensures that carbon dioxide is not released into the atmosphere, right? So that's avoided emissions from the geosphere. A second approach, right, is avoided emissions or emissions reduction from the biosphere, right? And these are things like ensuring that trees, for example, are not being cut down, because when we cut down trees, it results in a release of carbon dioxide, right? So this is often called avoided emissions, right? We have a program called RED Plus, which stands for Reduction of Emissions from Deforestation and Degradation. And that approach seeks to ensure that CO2 is not released into the atmosphere as a consequence of the felling of trees. Again, a salutary policy, but it does not constitute carbon dioxide removal. A third approach that does not constitute carbon dioxide removal is emission reduction from the geosphere with storage. This is carbon capture and sequestration. And in that case, what we're doing is we're utilizing a technology that captures CO2 at the point source of combustion. For example, if you have a coal-fired power plant that's burning coal, it would then release CO2 into the atmosphere. But if you have a carbon capture and sequestration system, which essentially is a filtration system, you can capture that CO2 before it is released into the atmosphere and then pressurize it, ship it for storage, or utilize it, right? That is again a potentially salutary policy, but it is not carbon dioxide removal because it is capturing that carbon dioxide before it has been released into the atmosphere. And then the final category that does not constitute carbon dioxide removal is carbon removal utilizing existing systems or processes, right? For example, if you have existing tree stands that are taking up CO2, that is not carbon dioxide removal. It is not an additional process to remove CO2 from the atmosphere. Nor are CO2 fertilization effects, right? CO2, for example, can stimulate the production of vegetation, which can be salutary, again, in terms of taking up CO2, but that is not carbon dioxide removal because it does not involve an active anthropogenic intervention into the system. Okay, so with that in mind, let's now move on to talk about why there is so much interest in carbon dioxide removal. And when we think about CDR, we have come to recognize CDR as having three potential roles to play in terms of carbon processes and climate policy, right? The first is in terms of the near term, in terms of reducing net emissions levels. The second is in terms of the midterm, which is balancing residual emissions, which is a term we'll define in a moment, to help reach net zero emissions, which is also a term we'll define in a moment, and long-term objectives to achieve what we call net negative emissions. And we're going to look at each one of these in turn. So let's talk about the first of these, which is near-term rationales for carbon dioxide removal. So carbon dioxide removal can help reduce current net emissions levels, which can buy society additional time to decarbonize. And as a consequence, it can help us avoid passing critical temperature thresholds. So under the terms of the Paris Agreement, the parties to the treaty pledged to take measures to hold temperatures to, quote, well below 2 degrees Celsius, which is about 3.6 degrees Fahrenheit, and at least aspire to hold temperatures to below 1.5 degrees Celsius. And at the 26th Conference of the Parties in 2021, the parties resolved to pursue the more ambitious 1.5 degree Celsius objective. These objectives of the world community, as embodied in the Paris Climate Agreement, reflect the fact that exceeding these temperature thresholds could have serious negative consequences for both human institutions and ecosystems. And these are impacts that will escalate substantially as temperatures increase, right? So what we know is that if temperatures increase 1.5 degrees Celsius from pre-industrial levels, we will see serious impacts. And indeed, we're already seeing serious manifestations of climate change, even at temperatures of 1.1 degrees, roughly, above pre-industrial levels, right? But things get worse at 1.5 degrees Celsius. And especially if you're in vulnerable countries, in developing countries, for example, or countries that are just a few meters above sea level, right? Things become extremely serious, even at 1.5 degrees Celsius. But then those manifestations begin to escalate as we get to 2 degrees Celsius above pre-industrial levels, right? We see substantial increases, for example, of drought and extinction risks in the Amazon, massive losses of coral reefs, even larger increases of sea level rise. And then when we get to potentially 3 to 4 degrees Celsius above pre-industrial levels, we begin to see massive manifestations of climate change. However, while the Paris Agreement recognizes the need for nations to, quote, reach global peaking of greenhouse gases as soon as possible, right, to try to not pass these critical thresholds and to undertake rapid reductions thereafter by the terms of the treaty, the world community's record in this context to date is extremely disheartening. Since the Paris Agreement entered into force in 2016, emissions have risen globally by approximately 7%. And the rate of increase of greenhouse gas emissions has actually accelerated over the past decade, despite the existence of this treaty. Rising carbon dioxide emissions, in turn, has led to rising concentrations of carbon dioxide in the atmosphere, which leads in turn to temperature increases, as you can see here. So now the global mean surface temperature in 2023 increased to 1.5 degrees Celsius above 1850 to 1900 averages. And 2023 was the warmest year in the 174-year observational record, clearly surpassing the previous warmest years of 2016 at 1.29 degrees Celsius, and then 2020 at 1.27 degrees Celsius. The past 9 years, between 2015 and 2023, were the 9 warmest years on record. And when we look at 2024, it is slated to be either the warmest year on record or the second warmest year on record. In the longer term, the current policies and measures taken by nations to reduce greenhouse gas emissions put us on track for temperature increases of well above 2 degrees Celsius, at least in terms of what current policies call for, right? There are optimistic scenarios, meaning that countries take all of their aspirations and actually implement them as law and then faithfully implement them in terms of reductions, right? But looking at what countries are actually doing at this point, the actual regulations in place to reduce greenhouse gas emissions, we are still slated for, according to many studies, at least a 2.5 degrees Celsius increase in temperatures. And so many of the extremely serious negative implications of climate change are likely to manifest themselves during this period. Carbon dioxide removal, as viewed as a method to slow down rising levels of atmospheric concentrations of greenhouse gas emissions. And thus it's argued that this would buy society time to decarbonize and potentially avoid maybe at least passing the 2 degree Celsius threshold. One particularly important reason to do everything we can to hold temperatures to below critical thresholds is that irreversible impacts may occur if we pass such thresholds. And some impacts, such as sea level rise, for example, will be baked into the system for very long periods of time. If sea level rises, for example, to a meter or more, it may stay at those levels because of the inertia of the climate system for 1,000 years or more, right? So we need to do everything we can to not pass those critical temperature thresholds, which in turn are tied to how high those concentrations of CO2 are in the atmosphere. And we clearly need some breathing room because at this point we'll likely exhaust our remaining carbon budget to stay below many of these critical temperature thresholds in the next few decades. A recent study concluded that we need to collectively reduce emissions by 43% by 2030 and 65% by 2035 in relation to 2019 levels to hold temperatures to 1.5 degrees Celsius above pre-industrial levels. In the short term, carbon dioxide removal is viewed as a way to potentially extend this carbon budget. And that's one of the primary reasons that policymakers are looking at it. A good way to understand this rationale is through the so-called bathtub analogy, right? So if you look at human greenhouse gas emission rates as a faucet, right? They are filling up a bathtub, right? And as that bathtub overflows at some point, if those greenhouse gas emissions continue, it will have serious negative impacts. At the same time, we have natural carbon sinks, right? Vegetation, for example, trees that take up some of that CO2 and help ensure that the bathtub doesn't fill up as quickly, but it's fairly de minimis. And so we view Action 2, carbon dioxide removal, as an additional way to hold the amount of water in the bathtub below levels in which it really overflows, and we start to see serious impacts. All right. That's why we view carbon dioxide removal as important in the short term, right? Buy us time so that we can decarbonize and not pass critical concentrations of CO2 in the atmosphere that in turn result in exceeding critical temperature thresholds that manifest themselves in very serious negative impacts. The second rationale for carbon dioxide removal is in the medium term, and this is to balance so-called residual emissions with remaining emissions of carbon dioxide when we reach approximately the mid-century. And this is to help us reach so-called net zero emissions goals. So to explain, the provisions of the Paris Agreement call for countries to achieve a balance between sources and sinks. Sinks are processes that remove greenhouse gases from the atmosphere. In other words, carbon dioxide removal approaches. And we want to reach that balance, so-called net zero, in the second half of the century under the terms of the of the Paris Agreement, right? You can see that in Article 4, right? Achieving a balance between emissions by sources and removal by sinks. And we have a large number of countries that have committed themselves to net zero, as well as a large number of cities and companies. This commitment to net zero and this acknowledgement of net zero reflects the fact that the global community likely cannot eliminate all greenhouse gas emissions, right, and get to absolute zero carbon emissions. And thus, sinks are viewed as a way to compensate for so-called residual emissions, right, emissions that can't be wrung out of the system by decarbonization, and thus, as a consequence, can facilitate society achieving so-called net zero emissions. So, residual emissions are largely a function of so-called hard-to-abate sectors. In such sectors, getting to zero in terms of carbon emissions may be impossible or very difficult to achieve. And this is due to a lot of factors, right? There may be technological constraints, right, where we just can't reduce all of the carbon emissions. For example, take steel. Steel requires very high amounts of heat for production. And for the most part, renewable energy cannot facilitate that, right? It may be possible in the long term through technological process that we find other technologies that will allow us to do that. But for now, we can't eliminate all of the emissions related to steel because we need fossil fuels to produce the levels of heat that are required for production, right? When we look at cement production, we face many of the same difficulties. Heavy-duty transport, it's very difficult to electrify aviation, for example. So there's going to be emissions associated with aviation fuels. We, of course, are trying to develop sustainable aviation fuels, but that is a long slog. And as a consequence, we believe there will be residual emissions from aviation for a long time. Agriculture. Many of the emissions from this are other greenhouse gases that are even more potent in terms of trapping outgoing radiation and thus exerting a warming impact. Things such as methane and nitrous oxide emissions. It's believed that removing carbon dioxide from the atmosphere through CDR approaches can help to compensate for those kind of emissions, and so on and so forth. It's been estimated recently that two of these hard-to-abate sectors, cement and steel, are responsible for a whopping 14% of global carbon emissions, right? So having an alternative that will help us to get to net zero by removing some CO2 from the atmosphere to compensate for not being able to absolutely zero out greenhouse gas emissions from these sectors can be very important. Overall, recent estimates are that somewhere between 10 to 20% of all greenhouse gas emissions may fit into this hard-to-abate category. CDR approaches are viewed as the primary sink mechanisms to compensate for hard-to-abate emissions and thus get us to net zero, right? And you can see that here, right, where every effort should be made to reduce our greenhouse gas emissions as much as we can, but we have to acknowledge that we're not going to be able to eliminate all of them, but carbon dioxide can help us to get at least to net zero in the medium term, right? If implemented at a very large scale, right? However, it should be emphasized that the amount of carbon dioxide removal that will be required during this period is critically premised on how swiftly global emissions can be reduced and how tenably we can address so-called hard-to-abate emissions, right? And that's something that's critical to acknowledge, right? The amount of emissions that are hard to abate is contested. Over time, new technologies may mean that we can decarbonize more aggressively than we thought before, and that could reduce the amount of carbon dioxide removal that's required to get us to net zero. So, as a consequence, the estimates of requisite deployment of carbon dioxide removal in the medium term range from a lower end of about 1.5 to 3 billion tons by the year 2050, and then some higher end projections that assume that hard to abate sectors really remain hard to abate, requiring us to remove somewhere between 4.7 and 10 billion tons of carbon removal to help us to get to net zero and help us to avoid passing critical temperature thresholds in the midterm. All right, now let's talk about the third rationale for CDR in the long term, and this is to achieve and sustain so-called net negative emissions. Carbon dioxide removal deployment can be important in the long term in several ways. First of all, net negative emissions later in the century may be critical to stabilizing temperatures at 1.5 degrees Celsius. What do I mean by net negative? I mean that more CO2 is being removed from the atmosphere than is being added to the atmosphere at that point, as we've begun to aggressively decarbonize. And indeed, all of the 97 scenarios investigated by the Intergovernmental Panel on Climate Change in its sixth assessment report that stabilize temperatures at 1.5 degrees Celsius require greenhouse gas emissions to turn net negative in the latter half of the century. That is, again, the drawdown of CO2 from the atmosphere is greater than the greenhouse gas emissions at that time. A second reason that CDR can be important in the longer term is that it can address so-called emissions overshoot. That is, the possibility that temperatures shoot above these critical temperature thresholds that we talked about, 1.5 degrees or 2 degrees Celsius, and carbon dioxide removal can be a way to draw temperatures back down by removing CO2 from the atmosphere. The warming the world experiences in the long term is in essence a largely time-invariant function of our cumulative CO2 emissions. So in other words, even if we stopped all emissions today, the world would not cool down substantially for many millennia to come. So if we ever want to bring global temperatures back down from whatever levels they reach when we get to net zero CO2 emissions, we need to actively reduce the amount of CO2 in the atmosphere that we put into it in the first place. Now, one thing that should be emphasized is that temperature overshoot and subsequent potentially drawing down those temperatures again through CDR is not a unalloyed happy story. It may be that when temperatures increase above these critical thresholds, we get irreversible sort of impacts, right? Loss of biodiversity, nonlinear climate responses. But it can ameliorate some of these negative impacts, and it's one of the reasons that we believe it is important in the longer term. And then a final long-term rationale is that carbon dioxide removal could also be used to restore atmospheric carbon concentrations of carbon dioxide to levels that are considered safer than they are currently. So what we know is that at current concentrations of CO2, which is about 420 parts per million, maybe a little higher, we're already seeing many negative manifestations of climate change. So many climate scientists advocate that we seek in the longer term to return our concentrations of CO2 to 350 parts per million, for example, or maybe even lower, such as 300 parts per million. And they argue that our historic climates were safer than our current status of climate. Without carbon dioxide removal, even if we pretty aggressively decarbonize our economy, given the inertia of the system, it could take 1 million years for climate to return to its pre-industrial states of atmospheric concentrations of CO2. So carbon removal could goose us toward those safer concentrations in the longer term. Overall, current research indicates that we will need very large amounts of carbon dioxide removal by 2050, and perhaps far more by 2100 to meet climate policy objectives, right? And that is the policy environment in which we operate. So with that in mind, let's talk about the current status and future needs of carbon dioxide removal. So one thing that should be emphasized at the outset in this section is that current levels of carbon dioxide removal are extremely modest. Current CO2 removals total about 2 gigatons or billion tons a year, of which 99.9% comes from the so-called natural climate solutions, such as afforestation and reforestation, and 0.1% from engineered approaches. It also pales in comparison to what we need, right, which may be as much as 10 gigatons by 2050, right? So when we look at that 10 gigaton goal, right, we may be at 0.10% of that goal currently. And we may need to avoid even 2 degrees Celsius as much as 20 billion tons of CO2 to be removed from the atmosphere by 2100, in addition to decarbonization, right? One thing that's sobering is that what we know is that we are going to need large amounts of mixed approaches or technology approaches to get to that point. We are not going to be able to get there with nature-based solutions alone. First of all, nature-based solutions are easily reversible, right? If you look at planting of trees, for example, climate change is one of the biggest threats to nature-based approaches to store carbon dioxide. It results in forest fires and increases in bark beet infestations, right, that kill trees, right? Also, it saturates, right, within 30 to 50 years. And we know that we need carbon removal that is on a much longer time scale, right, to compensate for our releases of carbon from the geosphere, right? And right now, we are looking at some at least mixed-based approaches that are giving us carbon removal with biochar, one of the approaches that we'll talk in a subsequent lecture on, providing about 81% of all of our sales of carbon removal, right? But in the longer term, right, we're going to need substantial amounts of these other technological approaches to get us to where we need to be, right? This may include marine approaches and direct air capture, and so forth, right? In the longer term, we're going to need what we call a portfolio approach, right? Where we can do some of these approaches at large scales, but not at scales that become unsustainable. And we're going to need to supplement those with other approaches if we ultimately require huge amounts of carbon removal. And that's a major challenge, right? Because we're at very early stages of being able to deploy most of those approaches. And so in the next two lectures, I will talk about what some of the challenges are in terms of those approaches. And with that, I will conclude this presentation. Thank you very much.